You're listening to the news. An earthquake goes off. Millions of people are killed. Everybody's in panic. They're sending the Red Cross over. Earthquakes. How do they work? What do you have to worry about with them? Well, we don't have too many earthquakes here in New Jersey, but once in a while we do. We had one back in 1884 that toppled chimneys and pushed houses off of foundations. You can imagine around here if we have earthquakes, they would do a lot of damage because we're not ready for them. So let's think about how earthquakes work. Earthquakes start off with a fault. All earthquakes come from faults. The fault sits there, it builds up stress and builds up stress, and bang, it slips. And it slips in one little spot. And as it slips in one little spot, that slippage is an earthquake. So basically, if you think it's breaking rock, and that's what causes it. So the same sound you hear from snapping a piece of chalk or breaking something, basically that's analogous to an earthquake. What happens when the earthquake goes off is it shoots waves in all directions. Now, some of the waves that come down are called surface waves. What do they look like? If you throw a pebble onto a pond, you'll notice that it gets those rings that come out in all directions. Those are surface waves. And the same thing happens around an earthquake. You get those surface waves emanating from the earthquake spot. Those are one kind of wave. However, there are other waves called body waves. And these will travel in all directions. The ones you see on the lake only are traveling on the top of the lake. These other kind will travel every which way, so they have more of a spherical path as opposed to the circular path of what comes off of a pebble. As these waves come out, then that is what causes the damage. They pass through things that aren't used to having waves pass through them, and it shakes them or jostles them, and bang, down they come. And most people get killed because what they're living in falls on them, not because of the waves directly. So therefore, that's the real damage of an earthquake. Now, understanding those earthquake waves, we can then predict where areas would be harder hit. We can engineer structures so that they won't fall over during earthquakes, and you can see big things change. Just recently there was an earthquake in California of a 6.5 on the Richter scale, killed 3 people, and that wasn't very many. On the other hand, a week later there was an earthquake in Iran, and it was a 6.7 on the Richter scale, almost the same. It killed 35,000 people. So you can see it mostly has to do with the engineering that really makes the difference between how people are going to survive or not. What we're going to do is, by understanding those earthquakes and being able to predict where they are, that's how we can prevent deaths. And obviously in California they're doing a real good job if only 3 people died from a 6.5 earthquake. So that's what we'll do, is we'll go through step by step some of the things that you have to take into account when you deal with earthquakes. Okay, the first exercise you're going to do today is we're going to look at seismograms measured from seismographs all over the earth to try to determine the exact location of where an earthquake went off. First of all, we can see on the first page we have a picture of a seismogram, and notice that it has 3 arrivals on it. It has, you can go along and you see there's really nothing happening on the seismograph, the needles aren't going anywhere, and all of a sudden, boop, up go the needles. And when they boop, up go the needles, that's the P wave showing up. Okay, and so we can see here it's labeled P, and it has a time below and says when that P wave first arrived. Now if we continue on, we see another spot labeled S, and it's right when the bobble first goes up, that's the second arrival. S, remember, stands for second wave, and we look down on that, and down below it comes in another time that we can measure off as when that thing arrived. Finally, there's even a third one. They label it L. This is really a surface wave. L stands for love waves. Love and Rayleigh are 2 surface type waves. And you can see those things that really make the needle go up and down. And that's what does most of the damage. But nonetheless, we have different waves arriving at different times. The S and the P wave, which are body waves, showing up first. And then the L waves, which are surface waves, showing up later. So here we have record, taken from a seismograph, of what the earthquake did. Now, with that information in mind, we can figure out how fast earthquake waves travel through the earth. And what we'll do is we'll turn to the next page, and we will see that we have a table full of data. Okay, and this has a bunch of arrivals on it. The first column of the table shows you the city where the seismograph was located, okay, from this first earthquake that took place in New Guinea, where the seismograph is located that we measured it from. The second column shows you distances, okay, and this is the distance from the earthquake epicenter to where your seismograph is to measure. Notice that there are three, at least two in most cases, but up to three different rows for each one of these cities. Each one of these then is going to represent the distance for each of the waves. Okay, so in three means that you have three waves that you've seen, three arrivals. If there's only two, you might have only seen two waves at that point. But then in the third column, you can see the time it took from when the earthquake first occurred to when you got it on your seismograph, when it showed up on the seismograph. Then that gives you a speed. Okay, and so you can determine how fast these earthquake waves are actually traveling. And what we're going to do is we're going to take this data from the data table and we're going to pull it down onto this graph. And notice this graph is just a grid at this point, but it has two components on it. On the vertical axis, you have the travel time of the wave. So to get from the epicenter all the way out to your seismic station. So at vertical axis, travel time. On the horizontal axis, you have the distance. Okay, so we can plot then the distance, which we have on for each one of these, that's the second column in, versus the time, which is the third column in. And you can already see down in here for the Australia station, which is where you had the first seismogram from, you can see that there are already three red dots on there. If you look at it, the top red dot, which means it took the longest time, is the L wave. That's the surface wave. If you look at the middle dot, that's the S wave. The bottom dot, which means it took the shortest amount of time, that's the P wave. So each one of these dots represents P, S, surface waves. Okay, so what we're going to do now is we're going to take the information from this chart up here, from your data table, and we're going to plot them all on this graph and make a graph of travel time curves. Okay, so we will have three travel time curves for P waves, for S waves, and for surface waves. So what we do is go down below, and we can see, we read the numbers off of here and the distances, find the distance down in here for 950. The next one down says 950 kilometers away. We find 950 on this horizontal axis. Then we look at the distance, the time it took. So 2.2 minutes, we read up on 2.2 minutes and put a dot. And we go to the next one, and it says 4 minutes. So we go all the way up to 4 minutes, and we put a dot at this 950 kilometer distance. And finally, it says 4.1 minutes, so we put our third dot at 4.1 minutes, and now we have the second piece of this curve. So what we'll do then is we'll do that for all the stations, and then we're going to connect the dots up, okay, and we're going to make the three curves. All right, now this information gives us kind of a standard grid then, some information on how then we can apply this to real earthquakes. Okay, now we're going to go and we're going to look at a real earthquake that occurred someplace in North America, and we're going to figure out where it is using this information that we've already collected. If you look on the next page, you can see that there are three seismograms stacked on top of each other. First seismogram is from Sitka, Alaska. Second one is from Charlotte, North Carolina. Third one is from Honolulu, Hawaii. Now what you'll see on these, again, you can see that the curves go along, and all of a sudden that first arrival arrives, and you can go along and see where the second arrivals are as well. What we're going to do to start with is to identify which is the P wave arrival and which is the S wave arrival for each one of these seismograms. That's your starting point. Second thing you're going to do then is you're going to try to put the time on each one of these P and S wave arrivals. And you'll notice that across the bottom of this picture, you have times. Okay, and so what you do is you figure out where the arrival comes in, up on top, and then drop down and see what time it came in at. Okay, with that information, you will then fill out the form down below here that shows the different locations. So you'll fill in the time for the P wave arrival and the S wave arrival for each one of these three stations. After that, you're going to subtract the times and figure out how long the gap in time is between the P wave arrival and the S wave arrival. Once you do that, we can have a gap distance, and for example in here, if we look at this versus the next one, it might be something about, say it's 4 minutes, okay, for example. We take that 4 minutes and what we do is we go back to the page that we just filled out with our travel time curves. And now we look down and we find where 4 minutes occurs on this sheet. And what we're looking for is a gap in time between the P and the S. So we go along the curve in a vertical fashion and see where there is a time delay from P wave to S wave of 4 minutes. And I come up with about 2,300 kilometers. Okay, so that's maybe, so again, where this is I'm not telling you exact answers, but it's maybe 2,300 kilometers. What I do is go back to the next page, and you'll see on question 18, the next one down, it says, what's the distance? Okay, and I just determined it was 2,300 kilometers, so I'm going to write in 2,300 kilometers. Okay, now I'm going to do that for each one of the stations to find the distance that it was from the epicenter of the earthquake to the recording station. And that's what goes on here. Now the next thing I'm going to do once I get those done is I'm going to turn to the last page, and there is a map of the northern hemisphere, at least part of it. Okay, and you can see on here it has latitude lines and longitude lines. What we're going to do is now we're going to plot up the locations of all of the stations that we just saw, the Sitka, the Charlotte, and the Honolulu. So what we do is we go down here on question 19, you can see it's got the longitude and latitude lines. So for example, Sitka's at 57 north latitude, 135 west longitude. So we go up here and we start measuring off until we can find 57 degrees north and go across the bottom until we find 135, and I can plot a little point, and that becomes where Sitka is. Now what I'm going to do is I'm going to make a circle of where that earthquake could have come from relative to Sitka. And what I do is use a compass, and I go to the scales at the bottom of the map. I want to move this compass until it lines up with about 2,300 kilometers. Okay, and so now I've got this radius of the circle is 2,300 kilometers. And what I do is I put the point of the compass on the location, and I draw a circle on my map. Okay, now they have a circle on the map, and this circle has now a radius. That means the distance any place on the circle to Sitka is 2,300 miles. And what that means is that that earthquake occurred any place, I don't know where, along that circle. Now obviously that's not going to be particularly useful because that's too big an area. So what we do is we make circles for each one of the three locations. Okay, and where the three of them come together at a single point, that is going to be where the epicenter of the earthquake is. Okay, and so we can figure out exactly where it went off. Now that will tell us that we have a fault there and that it's an active fault. And that means then that we will know to be able to set up our building codes, watch out for hazards, things like that in that area, because we know that that fault can produce earthquakes in the future and that it has to be monitored. There's one other thing about earthquakes that you should know. You know, you talk about the damage that they do. Obviously, that's the most important thing. How much damage are they going to do? Well, certainly the size of the earthquake has a big function of how much damage it's going to do. Big earthquakes, big damage. Okay. However, it isn't only just the size of the earthquake. It's also the material in which the waves pass through. This was particularly true. We had an earthquake back in 1989 they call it the World Series earthquake. It occurred during a World Series game out in California, Loma Prieta, which was about a 7 on the Richter scale, I think 7.1, and which did a lot of damage to the San Francisco area. Now what they found was that certain zones, the Marina District, for example, as they call it, had a lot of damage. Other areas didn't have so much damage. Why is that? The reason is what the area is made of also greatly affects whether you're going to have damage or not. The way it works is typically if you have hard rock, solid rock tends not to get too much surface wave action. Okay, the surface waves have trouble moving around something that's solid. Wet, soft material, however, will roll like ocean waves. And so therefore, if that's going to roll like an ocean wave, you can imagine a house won't do real good if it has an ocean wave going through it. And so that's what we have. That's why you have the differences. Now, the first exercise we're going to do with regard to location being good or bad is the one on the Marina District for this 1989 earthquake. So we look down at the picture and you can see there are seismographs located X, Y, and Z on this map. And noting them, it shows you what the difference is in how much movement you had on the seismograph. Clearly, the more movement, the more damage to buildings. Less movement, less damage. So therefore, what you're going to do in this exercise is to be able to look and determine what area would be better for you to live in and less damage as opposed to other areas. Okay, now once you get that done, you kind of look at this and understand that it's the hard rocks that are really solid and the softer stuff, which is really going to be more dangerous. Then we're going to go over and do something a little better on the handout you got, which shows you a map of New Jersey, of the Newark area, and shows you the distribution of the different rock types, whether they be soft sediments or muck, which would cause a lot of damage. And so you can then decide if an earthquake went off here, where would you be best to be located not to get hurt? Okay, and so therefore, since we don't have a seismically active area, this isn't that important. But if you move out to California, you might want to keep this in mind. So that's the next exercise, is just to look at locations. Here's one with data. Here's one just knowing what the data told you from California and applying it to say where would be a good spot to live and where wouldn't.